All right, now we're going to define the magnetic force. So we know that electric fields exist, and if you just place a charge in an electric field, it's going to feel a force via F equals QE. Positives go with the field, negatives go against. But for magnetism, the magnetic force is actually different. So to experience a force, a charge actually has to be moving perpendicular to a B field. So this is known as the Lorentz force law. The magnitude of the magnetic force experienced by a particle is QV perpendicular B. And there's actually a cross product going on here. The full force is F equals QV cross B. I like to think about it this way. So it's Q times some perpendicular aspect of V and B. It's usually easier to find the portion of velocity perpendicular to the field. In 90% of cases, this is just QVB. We'll deal with direction later. So this is counterintuitive because you actually can't get a force on a particle if you just place it in a magnetic field. It has to be moving, and not just moving perpendicular to the field. So to get no magnetic force, particles can be not charged, not moving, or not moving perpendicular at all to the field. So if there's a magnetic field to the right, and the particle's moving to the right, no force. But if the field is to the right and the particle's moving up, there will be a force. So here's a contrived case where we're just showing that only part of the velocity matters in this. So determine the magnitude of the magnetic force experienced by this particle, given that there's a field B pointed to the right and its velocity V is oriented at this angle and its charge Q. Well, we know that the magnitude of the magnetic force FB is equal to Q times V perpendicular times B. Alrighty, simple enough. So now let's look at it. So this velocity component is getting completely ignored. The parallel component gets entirely ignored. The B field does not act on, it does not care. It does not care if you're moving parallel to it. What it does care about is the velocity perpendicular to the field, V perpendicular. So what is that? It's Q times, well, notice V perpendicular does not touch this 30-degree angle. So does not touch means it's opposite. So we should be using sine. And oh, look at that. I am so cool and so nice. This is such a nice unit circle angle. Because what is sine 30? Sine 30 degrees is just 1/2. So I get Q times 1/2 V times B. So 1/2 QVB. That's usually not the issue with magnetic force. It's usually not the magnitude. It's the direction. So now we're going to formally introduce this with the cross product and the right-hand rule. So we're going to be doing everything in 3 dimensions because the magnetic force uses an operator known as the cross product, which takes in 2 vectors and it spits out a third vector perpendicular to both. So if V is in the X and B is in the Y, then the force is in the Z. So your V, B, and F actually make a 3D coordinate system. So you get all 3 axes represented with this. So remember that we usually just live in this world of I hat being to the right, J hat being up. Well, now we're going to be representing 3D. So we have K hat. So positive K hat is represented with a circle. And that means that the field is sort of pointing at you. So if it points at you, you can think of it as like the tip of an arrow coming at you. But conversely, into the screen or into the page would be negative K hat, and that's an X. So think about shooting an arrow into the screen. If you shoot an arrow into the screen, what you'd be seeing is the feather. So this is like the feather of the arrow. So again, they think of it like Think of it kind of like this, where it's your arrow. You have like your little arrowhead, and you got the feathers on the end. So you'd see the dot if the arrowhead is coming at you, and you'd see the X if you're on this side, and the feathers going away. So here's the right hand rule. I will show you my version. Everyone has their own right hand rule that works. I like this one. This one says, this has to be your right hand, by the way, because there's going to be two choices. Because we know that like if your V is in the X and B is in the Y, FB is in the Z, but there's actually two options. It could be plus Z or minus Z. So this helps you pick the right one. So your thumb is going to point in the direction of V. So just match it with your paper. If V's to the right, point it to the right. If V is into the page, point it into the page, into the screen. So that's what your thumb does. Now, you use the rest of your fingers to represent the direction of B. There are usually many field lines for your many fingers. And if you do this, your palm will point perpendicular to both. So notice in this example, their thumb points in the X, their fingers point into the screen, which would be negative Z, and their force points straight up, which would be Y, plus Y. Now, if you've learned from like a mechanics background, this one, where you're a fan of making a 3D coordinate axes system out of your index, middle, and thumb, you can do that too. I struggle with this one. I'm not a big fan of it, but I always include it because some people really love it. I would say most of my class does the first one, but there are some diehard finger gun enjoyers. And this one's funny because you can remember that magnetism is your middle finger because you're giving a nice middle finger to magnetism because it's so annoying and you actually have to use your hand. Negative charges, be careful about negative charges. Negative charges do the opposite of positives. So I just use my left hand. I'm a big fan of just using my left hand if it's a negative because that auto flips it for me. I cannot tell you the amount of times I get stuff wrong by using the wrong hand. So let's do some examples. We just want to indicate the direction of magnetic force. So here, my V is to the right. So using my right hand rule, I take my right hand and I stick my right thumb to the right. So I'm pointing my right thumb to the right. B is out of the page. These are the arrowheads, so it's coming at me. So I'm going to point my fingers at me. And notice, as a result, my palm points down. So my magnetic force is down. All right, what about here? It's a positive charge, so I use my right hand. Positive charge again, use my right hand. I point my thumb to the right. B field is up, so I point my fingers up. And notice my palm, it's coming right at me. Since my palm is coming at me, someone is shooting an arrow at my face. So that would be this, which is out of the page. Plus Z. All right, negative charge. Use your left hand or remember to flip. I am going to take my left thumb and stick it straight up. My fingers point to the left. And notice now my palm is actually pointing into the screen. So I'm shooting an arrow into the screen. So I would be looking at the feather. So this is going into the page. Notice if you try this with your right hand, up, left, I would get at me, which would be out of the page. So you'd have to flip it or just remember to use your left hand. All right, similar idea here. I'm going to use my left hand. V is going up. B is going into the page. So my fingers point at you or into the screen. And notice that that's going to point to the right. So this would be to the right. All right, positive charge. So I'm using my right hand, point my right thumb to the right. B field is down, so I point my fingers down and look at my palm, points into the screen. And notice in every single one of these scenarios, I have created like an XYZ coordinate system. All right, this is funky. V is out of the page and it's a negative charge. Okay, so V is out of the page. So actually my thumb points at me. So my thumb points at me and B is down. So my thumb is pointing at me and B is down. So my palm actually points this way to the left. We'll hope the mirroring in the video is correct. If not, we'll have to translate. And then we have a couple funky cases. So let's just zoom out here. All right. Notice that we have made a 3D coordinate system in each case. Velocity was x, force was y, b was z. Velocity was x, force was z, or sorry, velocity was x, b was y, force was z, x, y, z. X, y, z, x, y, z, and so on. X, Y, Z, X, Y, Z. So you actually should get all three dimensions, unless if you have like an angled force. All right, here's some special ones. So I stick my thumb to the right. It's a positive charge, so I'm using my right hand. Then I stick my fingers to the right, and I am severely struggling. You can't do it. Right? I can't. Like, as if I try to twist my hand that way, it doesn't work. Well, realize that that's a feature, it's not a bug. Because this V points in the same direction as B. And we said that FB is equal to QV perpendicular times B. So if you're exactly parallel to the magnetic field, you experience no force. You can't contort your hand to do it. So this is actually zero. It's actually zero force because F is parallel, sorry, V is parallel to B. All right. And here we can actually get a combination. So we know the force, field, and velocity have to make a 3D coordinate system of mutually orthogonal vectors. So it's going to be something that's 90 degrees with V and also perpendicular to this field. So there's actually two options. It can either be this one, 90, or it can be this one, 90. So which one is it? Well, just use your right hand rule. Just use your right hand rule. V points up and to the right. So my thumb is up and to the right, and it's my right hand because it's a positive charge. Then I just point my fingers into the screen. And if we look at what my palm is doing, my palm is pointing up left. So it's going to be this. It's going to be this. It's going to be this right angle as opposed to the other one. So it's going to be left plus up. So you can get it to be a force with components if you have a weird velocity like that. All right, here's a review. Draw the direction of the electric force on each of the particles. Well, this is really easy because remember that positive feel a force with E and negative charges go against E. So don't think you have to do right hand rule just because you learned it. So if you have electric fields, this was just sources and sinks. This goes back to our basic unit 2 stuff. All right, pretty standard. Electric field is up. It's a positive charge. So this force would be up. Negative charge. Negative charge experiences a force opposite of the downward field, so this would be up again. Negatives accelerate opposite the E field. Positive charge. E field is out of the page. Positives experience a force along the E field. So if E is out of the page, positives would feel a force out of the page. Okay, that seems kind of random that I included this, but this is because a very important problem we can do is we can actually use electric and magnetic fields together to allow particles to move at constant speed. So we call this crossed fields. And crossed, coming from perpendicular. I don't know what other definitions you'd be thinking of for crossed, but by crossed we mean perpendicular. So if you have perpendicular E fields and B fields, it's actually possible for all the forces on your charge to cancel. And how do you do that? Well, they have to be oriented in a special way, and I kind of find it a fun puzzle. It's some of my favorite problems is to figure out which way the fields have to go. But the magnitude is also really easy because the QVB magnetic force has to cancel the QE electric force. So let's do a basic example here. A point particle, positive charge, is moving at a constant velocity v to the right. So constant velocity v. So this means that there is no net force. It says that there are uniform electric and magnetic fields which are perpendicular to each other. And I'm giving you the magnitude of the E field as E. Ignore gravity. So we're using these small spheres, so we can always ignore whatever is happening with gravity. Because we said that at those scales, the electric force absolutely dominates electric absolutely dominates gravitational effects. Okay, what's the direction of the electric field in this region? Well, I have a positive plate and a negative plate. E fields point from positives to negatives, right? This is just our sources and sinks rule. So the electric field E is just straight down. Positive plate is a source of field lines, negative plate is async. What about the magnetic field? So this is where it gets more tricky. So I always like to just draw myself a free body diagram. So my positive charge is going to feel attracted to the negative plate because there's an E field pointing down. Positive charges feel E electric forces down. So there's going to be an electric force that points down. Okay, very cool. So it's moving at constant velocity. So that means the magnetic field must perfectly generate a magnetic force that cancels. So it is a very common mistake to say the magnetic field points up, which is really close, right? Something points up, something magnetic points up, but that's the force, not the field. So we just get to play a reverse of our right-hand rule game to figure out what field it is. So we just have to ask ourselves, how do I get my force to be up? So it's honestly easy just to guess because it's a 50-50. Just try the right-hand rule. You know it's going to be into or out of the screen because you're missing, that's like you're missing direction here because you have an X and a Y, so you know it's going to be one of the Z's. But again, we don't have to guess. We can just reverse it. So we know that our force is up. Force was your palm, and this is a positive charge. So my palm points up, and my thumb points to the right. So thumb points to the right because V is to the right. Palm actually points up because I know the force this time. And by default, that has made my fingers point into the screen. So actually the B field is into the page. And again, you can quickly check that works, right? QV, cross B, yep, pushed up. Positive charge feels a downward electric force, so magnetic force must be up to cancel. And by right-hand rule, also you can say, like just using right-hand rule, You don't have to like say, I point my thumb to the right. And no, we understand what the right hand rule is. Please say, like, we don't need you to, I've said, we don't need you to mansplain the right hand rule. You can just say you used it to figure out that if FB was up, B had to be into the page. All right, let's find the B field in terms of E and B, or E and V, sorry. So the forces are balanced. So what does that mean? Well, if the net force is 0, that means that the magnetic force and the electric force have to cancel each other, right? That's what our Newton's first law equation from this free body diagram says. FB is QVB, because we're all nice and perpendicular, and FE is QE. And this is not obvious to a lot of people, that these problems actually have no reliance on the charge. So the charge actually cancels. So we get VB is equal to E. So the magnetic field B is going to be E over V. And that's what's needed to balance your forces. So if your charge goes too fast, the B field will win. If your charge goes too slow, the E field will win. So we'll see later this can be shown as like a velocity gate, where only a very special speed can pass through the plates. And that's very useful for us in the next section. All right, so now we want to find an expression for the magnitude and direction of the missing field required for each particle to move at constant velocity. And it says ignore gravity. Well, if it's moving at constant velocity, we know the force is balanced. So let's find what force we're given. So positive charge, so QV, cross B, up. So we're actually going to experience a force QVB up. Okay, pretty straightforward. That's just business as usual, right? QV, point my right thumb to the right into the page, so I got up. Okay, cool. So that means that to cancel, the electric force, QE, must be down. So we can set those quantities equal. QVB equals QE. So E is equal to VB. But we also want the direction. And we know that positive charges experience a force with the E field. So I can say that the electric force direction matches the electric field direction. So this would be VB down. All right, same idea here. So now we have a negative charge. So negative charge moving to the right. So I have my left thumb pointing to the right. B field is up, so I stick my fingers up. So that means my palm is going to point into the screen, right? QV, and then B is up. So bam, into the page. So we actually get a force QVB into the page. So this means our electric force must be QE out of the page. So kind of a funky free body diagram, if we want to call it that. So we do get the same answer as before, right? If we set these equal, we're still going to get E equals VB. And then we have to think about the direction. So this is a negative charge. So since it's a negative charge, if we're experiencing a force out of the page, that is opposite the E field direction, because negative charges accelerate opposite the E field. So if we're having an out of the page force, there must be an into the page electric field. And actually, this should not depend on the sign of the charge. So I do believe that if we just pretended the charges were positive, due to some double negative tricks, I do believe you'd get the same result. Yeah, we could quickly verify that. What if it was positive? If this was a positive charge, we'd get QV cross B. So I get a magnetic field that points towards me, so out. Yeah, so I need a field in. So these velocity selector ideas actually don't require the sign of the charge. All right, this is an E field. What do we know about E fields? Well, we know in this case, we're going to experience a force QE against the E field, because negatives accelerate opposite the electric field. So that means our magnetic force, QVB, which is the magnetic force, must be up. So we can set these equal. QVB equals QE. And we get a result we solved for earlier. If we solve this for B, we would get B is equal to cancel, E over V. Now, the reason the magnetic version of this is harder is because you got to right hand rule it. So it's a negative charge. So I'm going to use my left hand. My velocity is to the left, but my force is up. So my palm points up. So this means my fingers are actually going to point at me. So this would be out of the page. And notice if you did it with a positive charge, you'd still get the same idea because you'd get QE up, so QVB has to be down. Yeah, it agrees. And then last case for this, electric field points out of the page, and it's a positive charge. So we know that we're just going to experience a force QE. It's going to be out of the page because electric field exert a force parallel to the field in the same direction on positives. So by cancellation, QVB, the QVB force must be into the page. They cancel, and as before, we saw B was equal to E over V. So now we can work this out. So my velocity in my right hand points to the right, and my magnetic force, so my palm actually points, my palm is actually going to point into the screen. So let's try to achieve that here. So palm points into the screen. Yeah, you see me contorting my hand here. So I got it right down. So it's going to be down. And we can check that, right? If I go right and then down, that does point into the screen. So it's actually going to be down. So again, how did I do that? I know I had to stick my right thumb to the right, and I had to stick my palm in so it points into the screen. So that means my finger's pointed down for B. So tricky, but very conceptual. All right, last we're going to do the classic velocity selector question. So we have a negatively charged particle, travels upwards between the plates of a charged capacitor at constant velocity. You love to see it. There is a 6,000 Newton per Coulomb electric field between the plates, and there's a 20 millitesla. So B is equal to 20 millitesla. So that's this. All right. Draw the direction of the fields and calculate the speed of the particle. All right, so sources and sinks. Sources and sinks tells us that the E field is just going to point from right to left, and this was 6,000 newtons per coulomb. Okay, so what does that mean? Well, this means my particle, my negatively charged particle, for one of two reasons, you can pick whatever is your favorite, is going to experience a rightward electric force, QE. You could say it accelerates against the E field, or you could say, well, the positives are to the right, so the negative is getting attracted to the positives. So that, of course, means for our usual argument that the QVB magnetic force must exactly oppose that. So how do we achieve that? Well, how do we achieve a leftward magnetic force? So I'm using my left hand. I stick my thumb towards the top of the page because that's the way we're going. And I know that my force is to the left. So I'm actually going to stick my palm to the left. And if I do that, well, we know it's going to be into or out of the page. So if I try into the page, my palm points right. So I need my field to point at me, right? So my thumb is up, but my force is to the right. So my to the left rather. So I stick my palm pointing to the left. So I see as a result, my fingers are ending up pointing at me. So this is an out of the page field. So we have a B field, which is equal to 0.02 Tesla. And you can also check this would work with a positive charge. So a positive charge would feel a force to the right. And if I do QV, cross B, sorry, positive charge feels force to the left. That's why I messed that up. We do get the expected result. Okay. Calculate the speed. Well, this is actually the easy part. We already found the forces. We already found the directions, which is the hard part. Now we just set them equal. This is the only thing we haven't solved for today is V in this arrangement. So we get VB is equal to E. So we get V is equal to E over B. This is known as the velocity selector relationship because you can select a very special velocity of your charge that can pass through. So our E field was 6,000 newtons per coulomb, and our B field was 0.02 Tesla. And through the power of magic, this is a meters per second. So how could you actually justify that? Well, we actually know that F equals, I'll do this in a different color. We actually know that F equals QVB. So we actually know that newtons are equal to coulombs times meters per second times Tesla. So if you actually worked out your units, here, you would see that a Tesla is a Newton per Coulomb meter per second. You know what, let's do that. We have time. We're not particularly pressed for time today. A Tesla, right, if I divide both sides by Coulomb meter per second, I would get Newton per Coulomb times meters per second. And oh yes, how lovely. Cancel, 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 cancel. And then you become a numerator. How nice. What a nice world we live in. All right, what is this? Well, I'm going to multiply by 5. No, I'm going to divide by 2. That's a 3. So I believe that this should be 300,000 meters per second as our speed. So that is a very large speed, but it's still several orders of magnitude off of the speed of light. So it's still reasonable. It is still very reasonable for that. Yeah, so that's kind of everything with just our basic right-hand rule. Next time, we'll actually talk about what happens if we have motion of particles that aren't just forced to be in a straight line.